I'm Alex Graf. I work on, my basic pattern is I work on things that I think should be useful going forward. I tend to implement them, and then everybody else follows suit. Right? Nesting, that worked. KVM on power, that worked. UEFI, even on embedded, that seems to work out well. I'm not always sticking around to see the end of that game, but I try to initiate a few cool things. This one is not thanks to me, though. This is thanks to Intel. So thank you, Intel, for giving me this talk, or allowing me to talk about something really cool. So what is speculation? You saw all the Spectre things and Meltdown and all the other things in the news. Speculation is something that's been around with us forever. So imagine this piece of code there, that's C code, where just a simple function, it goes, adds one piece of variable to a global variable, and then it returns the dereference of another piece of variable with another addition. Usually what you see when you execute code is assembly code or opcodes even. So the CPU, this whiteboard is pretty far up. This is probably, awesome. You see these numbers here. This is what your CPU reads, right? This is the binary code that your CPU reads. The human readable form is the one down here. It's very human readable because it's x86 syntax. So everybody knows that, obviously. The basic idea is you add this number to this pointer dereference, and then you move this register into this register, and then you dereference again an indirect pointer over into that variable and return. Add in between. Right? You also do an add in between to actually do the addition that we saw in the C code. What is important in that piece of code is not the actual semantics, because they're actually wrong. But is that what you see as a programmer, if you're working with the CPU, is that everything happens one thing after another. Right? You have one instruction, and then you have another instruction, and you have another instruction. And all of these instructions run sequentially, and you don't really see any interim stage. It's just all these things happen atomically and one after another. But that is not quite true in the real world. What really happens is that some of these instructions might take longer. Right? Some of these instructions might need to dereference memory, which can take forever. And because they take so long, you have a lot of time in between where you can basically do something else as a CPU. And what CPUs do is they basically open this other speculative context where they just go and keep executing instructions along the side while they're waiting for this other instruction to finish, so that by the time you're done, you basically calculated everything already, or you at least have everything cache hot, or you hope that you have things cache hot when you're at a later point in time in your instruction stream. So this is speculation in a nutshell. There's a lot more detail to it and a lot more complexity, but basically it means your CPU wants things that go beyond the code that you're actually running without telling you. And most of the time it does that really well. It's just that all the Spectre things showed you that it might have side effects. So what is the point of this? Why do we do speculation in the first place? We do speculation because accessing memory is slow. So these numbers are from a website. You can see the website down there, where they show you what the performance numbers look like for Skylake, for a typical Skylake server system. And you see that you need about 250 CPU cycles just to access a single piece of memory. Imagine you would not have anything in between that memory and your CPU. It would basically mean your CPU is constantly waiting for everything. So what people did is they added caches. So you have multiple tiers of caches. There's usually a level 3 cache that is reasonably big, but that one is not too fast to access. There's a level 2 cache that's a bit smaller, faster to access. And then there's a level 1 cache that is really, really fast to access, but very, very small. There's another caveat to this. The reason you have all these different layers with all these different things is, one, they have different processes which make them which indicate the performance. So the reason you have the different performance numbers is because fabrication-wise, the bigger they become, the smaller an individual entity is. So you can fit more into the same space. But they're also at different levels in your hierarchy. So level 1 is close to your core. Level 2 is usually close to your core cluster. Level 3 is usually close to your NUMA node, or maybe a combination of clusters. Depends on your CPU topology. And then memory is obviously, again, you have NUMA and all these other weirdo things. But this presentation is called L1TF and KVM for a reason. L1TF basically talks about this L1 thing up there. That's what we're talking about. So if we're looking at memory, you can't really talk about memory without talking about paging too, because in reality, if we're dereferencing this pointer, we're not actually dereferencing a pointer from our memory that we're talking about. We're dereferencing the pointer from a virtual address that does not actually live in our physical address, or that does live in our physical address space, but there's a mapping between those two. So what we see as a process is, we do see this really, really big linear address space where we can just roam freely and we are there on our own as an application. But as a CPU, what we really want to know is, if we're talking to memory, which address should we talk on? And in between those two, there's a mapping called page table entries. It's basically the paging mechanism in any modern CPU you have. So you have this mapping between your virtual address space down up here and your physical address space down there. And these page table entries are actually pretty cool. Because you find the page table entry, there's this radix tree there that basically allows you to walk through a couple of levels depending on your virtual address you dereference up here. So by the time you find that entry, you already know which address this is about. And then in there, you just have to write down what the physical address or physical frame number, the page entry here, is. And then on top of these, there's this data chunk that tells you what the physical address is. You also have a couple of attributes, like it says, is this user accessible? Is it writable? Should I do write through? Like, should I go through caches when I write, or shouldn't I? And the present bit. So is this an actual page table entry? Is this valid, or is it not valid? If you're looking at Meltdown, which we're probably going to have like next or the one after, don't remember. The problem with Meltdown is the U bit, that Intel in speculation just basically ignores the U bit. That is what Meltdown is about. L1TF is about the P bit. The P bit, when you don't set the P bit, it usually, architecturally, it gives you a page fault. So what is a page fault? A page fault means you stop your instruction flow at the instruction that faulted, that was accessing memory while it shouldn't have. And you're going into a cleanup process to do something with that exception, with a page fault. This is a pretty common process. You do that every day. It's used for copy on write, for example. It's used to slowly page pages into your memory. When you load a binary, for example, you don't necessarily load the whole binary at once. You load it in chunks, slowly one after another, because you might not need to load all of that binary into your address space or into your memory immediately. So how does paging work with our caches? We have our L1 cache, and inside our L1 cache, we have this piece of data now, right? But what does that piece of data actually contain? So on Intel, we have physically tagged caches, which means we have our data down here, and then we have a tag that says, this data belongs to this physical address. And the world is really, really easy and fun if we only have a single page table entry, because there, we just basically write this physical address down there. So this is the host case, right? And we know exactly what physical address this piece of data belongs to. Now, when you add virtual machines to that game, we usually have two levels of page tables. So what does the level 1 cache do with those? So now we suddenly, actually, what happens on the Intel CPUs, from what I measured, but I could be wrong, is that this tag down here actually still stays that tag. So we have a virtual physical address. And then you get another entry in your page, in your L1 cache that contains your host physical address as a tag. So these two things live side by side, and they just basically don't conflict. Don't ask me how they did that in hardware, but you don't get to see these host things from guest things because you're usually overlapping there. Now, what is this L1TF thing about then? So imagine you have a CPU. Let's take it easily, a single CPU. And that single CPU is running some secure code that contains some secure token, like your SSH client, right? Something that basically does something secure. Because it is running on that CPU, it wants to access that token really fast, which means it needs to it has that in its level 1 cache, because that's the only way to access data fast, or access memory fast. Now, on that same CPU, we can then context switch and have some other malicious code running. And that malicious code then could execute something like this. Imagine you have a pointer to some page that you control, and then you dereference another big list of Oracle pointers to depending based on the value of that number. This is public code. This is actually, you can see that in the Microsoft spec for L1TF. They basically write that down there. Now, what happens is, this is obviously assembly code for your CPU. And what happens is you're reading out, you're dereferencing that pointer, you write that into register, then you shift that register over, and then you dereference the Oracle based on that value into another register. So you're just reading data from memory into registers. What happens in a normal case? So this is the normal paging case that we had, right? We have a page table entry. The page table entry is there. Everything's fine. We are valid. Then what happens is we actually are accessing memory that is valid, right? We're actually accessing a real pointer, which means we now suddenly have 2 entries with the same tag in there. And we can just, as soon as we execute this instruction, we actually see our own data in this. So this doesn't help. What L1TF is about, though, is that we're doing something that is not normal. And not normal in our case means we're basically just saying this page is not present. But we keep all the other information. We still say we want to access this physical page, which means we're now getting a page fault, right? We're getting a page fault because the page is not present, but we still have this malicious physical address written in there. What does that actually do? Well, turns out, thanks to that page faults take a long time. You need to synchronize all of your state. You need to make sure the CPU is on the same level. Everything's aligned. They take a long time. What do you do when something takes a long time if you're a CPU? You speculate, right? So why shouldn't we speculate because we have a page fault? Well, we do that as a CPU. So we happen to also have that register, that physical number in our speculation context now, because we found this page table entry. It just triggered an exception. But we can speculate based on that, which means we now suddenly, in speculation context, we have our secret in this register. Can everybody follow that one? That's the crux of L1TF. Who cannot follow? Good, awesome. So we now have our secret in the register, which means all we need to do to expose that back is we shift it in speculation, we shift it into another register, or we shift it by a couple of bits, and then we dereference our Oracle based on that, which means we now prefetch our Oracle into our level 1 cache, because that's the whole point of speculation. We want to prefetch things into our caches to be faster. So we now have some data we control with which is dereferenced based on information that we really shouldn't have had in our level 1 cache. So how do we get that information out of that level 1 cache again? Well, that's really easy. We're getting an exception, we're getting our page fault, and after that, all we need to do is we need to see what takes longer. Does it take long to read these couple of Oracle array entries, or does it take long to read this one Oracle array entry? And one of our Oracle array entries is probably going to be fast because it's cached. And there we have just leaked a couple of bits of data. And if you loop that all over again, and you loop through your address space, you add 1 on 1, and you basically have, or you can read anything that is in your level 1 cache from another core from this malicious program. Now, there's another really, really cool feature on Intel CPUs called hyperthreading. So what does hyperthreading do? Hyperthreading basically means you don't have one CPU, you actually have 2 CPUs that in reality actually are one CPU. So you have 2 views onto the same entities of a CPU, because in most cases you don't make use of every single unit your CPU core has. You have a lot of different units that can be leveraged in a CPU core. And speculation is one way to fill those up with other work, but another way is to just basically have a second CPU exposed, and every time that one thread doesn't actually make use of your SSE unit, then the other thread might just make use of it, and you happen to to multiply the amount of code you can run on that single core. However, because they are running on the same core, really virtually, they are sharing everything there is to that one core, which includes your level 1 cache. So you now have not just one single entity that runs against that level 1 cache, but two entities that run against that level 1 cache. Which means if we now have our secure application running on one thread of one core and our evil application running on another thread of that same core, the secure application can write data into its level 1 cache or pre-fetch data into its level 1 cache because it's operating on some secure data. And the other thread could just loop in a page fault loop and directly read it out. We don't even need a context switch. We don't need anything in between. We can immediately see that data in that level 1 cache as it flows into its cache. So how do we mitigate all of this? It's fun to write exploits, and it's really fun to know how L1TF works. But at the end of the day, we want to be secure, right? We don't want to have others read our secure data. If I know my own secure data, I'm happy. If others do, I'm usually not. So how do we mitigate this? So usually, if we're looking at this single core environment, it's pretty easy, because if you're running your secure stuff and then you're running your evil stuff, you have a context switch in between them. You can't run two things at the same time on a CPU, really, unless you have threads, but that's a different. So you have this context switch there. And this context switch really means we're running KVM in between, because that guy can only run inside of a virtual machine to control its own page tables. So in here we have KVM, and KVM can just do something to clean it up, which basically means we can just flush our L1 cache when we go in, and then we're good. Right? We just don't expose our secret anymore. So we can leverage KVM to just clear our level 1 caches whenever we know that we would leak data. However, that multi-threaded case is pretty complicated. How do you make sure that this one entity that writes stuff without trapping and this other entity that reads stuff without trapping, how do you ensure that you can actually do anything about them, because you never get to see what they do? Well, the easy answer is you just don't. That's what we do today. So the current mitigation for hyperthread things is basically don't do it. If you want to be secure today, do not run hyperthreads. Just disable them straight away. But what does that mean, performance-wise? So obviously, everybody of us loves to build kernels, and my benchmark here is a kernel build. It's not a conclusive benchmark. It's not a really deep down, in-depth benchmark. But it gives you a rough idea on what a normal world application would benefit from hyperthreading and what it would cost. So this is basically the same kernel build, once run with SMT1 and once run with SMT2. So this is without hyperthreads, and this is with hyperthreads enabled. And the kernel build here took about 90 seconds. The kernel build here took about 75, which means we're having 15 to 20% speed up by using hyperthreading. So just the fact that you disable hyperthreads in some workloads, you can assume it would basically reduce your performance by about 30 to 0%. That's roughly the boundary you get. Some workloads benefit a lot from it, some don't. I think I could create a really contrived example where this number would be 50%, but that would really be a micro benchmark that is only to show that hyperthread disabling could actually hurt a lot. But in real-world applications, it wouldn't. In real-world applications, assume up to 30%. Now, one thing I did is, for this benchmark, I just basically said, let's just always flush the L1 cache on VM entry. And that one is about 1 second slowdown with the kernel build. Because we don't exit too often, but still, it is just simply fast to flush your L1 cache. If you saw the slide earlier, the difference between your L1 cache and your L2 cache was really just a couple of cycles. Your L1 cache is 4 cycles, your L2 cache is 12 cycles. So the CPU is really, really good at doing things asynchronously anyways, and speculatively, we saw all of that. So it can paper over the fact that we don't have everything cached in L1 anyways. Plus, if we're outside of our VM, we already did dirty a couple of our L1 cache. So not everything that is in the L1 cache actually does belong to data inside the VM anyways. So flushing the L1 cache is not too bad in my measurements. I heard of people that basically measured a 50% slowdown because of L1 cache flushes. So take that with a grain of salt. It's very heavily workload dependent. Now, maybe not everybody wants to lose 70% performance in the worst case. So what can we do instead? Well, there's a couple of alternative ideas. One is, if you have this scenario, right, you basically have these two threads. I said there's no event we can trap on. Well, that's semi-true, right? There is an event. This whole thing only works because we're doing a page fault. Without a page fault, there is no way you can trigger that speculation based on bogus data. So the guest actually, the malicious guest actually has to read out that data using the page fault, and after that run again to measure based on its L1 cache information. Now, if in between, or this is all running in a VM, so in between, what we can do is, as KVM, why don't we just go and in here fix things up and basically just flush our L1 cache every time we see a page fault on the guest? Well, there's two caveats. One is that is obviously overhead. You would still slow down your guest. And the second, even worse one is, well, there's another really nice feature called TSX. That's transactional memory. So with transactional memory, what happens is your CPU gives you this ability that you can run a sequence of instructions, and you only ever get to see it happen atomically, which means either all of those instructions virtually take place at the same time, or none of them do. There's a couple of technical ways to do that, but one side effect of that is that if you happen to take a page fault in between, the transaction just aborts without anybody noticing that outside. You cannot trap on that from a KVM point of view. So KVM has no idea that inside here there was a page fault, which means we don't have that event anymore, and well, there you go, right? You can read whatever. So that doesn't work. Oh, I forgot to mention one thing. That doesn't work because you could potentially disable TSX. You could just say, CPU, please just don't expose transactional memory. Nobody's using that anyways. And then trap on the page faults and you're safe. But modern Intel CPUs no longer give you the ability to do that. So with modern Intel CPUs, you cannot disable transactional memory anymore. So Skylake and above don't have anything to do that. And that's probably what people want to buy today. There's no chicken bit anymore. So from Skylake on, transactional memory is considered a legacy feature. Yeah, I agree. I had that look too. Nobody's using it, but it's a legacy, which probably actually aligns pretty well. So the other idea is, well, the other entry path we have into making things break is we have to have this page fault, which means we have to have a page that actually does not have the present bit set, but still a physical address that exposes a real physical address that we can align with on the level 1 cache side. Now, what we usually do is we have our nested page flow where up here we have our virtual machine that has its own control over its own page table entries. And then the hypervisor can only control the nested page. But there used to be another approach back in the day when the CPUs did not implement EPT yet. And that was called shadow paging, where basically we are fixing up everything, or we translating from our guest virtual address all the way to our host physical address using shadow pages. So we basically do the translation that the CPU would do for you with those two page tables in one go as KVM. And inside there, we can obviously fix everything up we like. Now, there is a caveat with shadow paging. Shadow paging was basically not used anymore as soon as EPT came around because EPT was just way faster. So that one alone basically lost about 30% performance. And one of the reasons for that is that on context switch, when you have one application switching to another application, you need to switch your page table entry, which is now a privileged instruction because your hypervisor needs to, instead of setting that page table entry to your real page table that you provide as a guest, it needs to set it to a shadow page table where it actually combined your guest page table with its host page table, right? There. We need to switch over to basically loop that via KVM. Now, what's worse is that thanks to Meltdown, we not only do that on every context switch, we even do it on every syscall. Because every time you're going into the kernel, you now need to switch your page table between the kernel view of the world and the user space view of the world, which ideally shouldn't be the same because Intel CPUs forget to check the U bit in speculation. So, so one idea to actually, it's not just once. It's I think 3 times after we changed the CR3 value, the page table entry, the page table pointer during syscall. Every time we go in and out. So what we could do is, that's an idea from Paolo. It's a pretty cool one. There is a feature in VMX that allows you to create CR3 whitelists. So you can actually tell VMX, look, these pointers, these page table pointers over there, these you can just write to CR3 and I wouldn't trap. And everything else would still trap. So you don't give guests access to page tables that it can modify itself, but you give the guest the ability to switch between page tables that you know are sane. And you can use that feature to basically, imagine you would power virtualize your guest kernel to not switch CR3 when on context switch directly, but do a hypercall where KVM would then return the shadow paging CR3 value for it, which means you can have the guest directly switch page tables for KPTI because it is aware of the shadow paging pointer, shadow page table pointer that it was actually trying to access. I guess I lost you guys, but this is fine. So this is one idea. We need to hurry up a bit. The other idea is what if the other thing that slows down shadow paging is PML, is our modification. So every time we modify the page table down here, we need to notify KVM to actually change its shadow page table entry as well. And what we could use for that is a feature called PML, the page modification log, which is used for live migration, really. So in live migration, what we have is we have a guest running, and we want to know what did the guest actually modify in between the last time I transferred its pages over to my destination. And we could use the same feature to know, did the guest actually modify any of our page table entries? Because that way we don't have to ever write protect our page table entries, because we can just lazily adapt our shadow page according to TLB flushes. There are more alternative mitigations that people are thinking of. We had this BOF yesterday where people are working on core scheduling, so you only ever run a VM based on cores and never on threads, with a couple of different ideas on how to do it. You could either expose threads in the host still, or even just completely not expose threads in the host, and but only expose threads in the guest like we do for Power. And another thing people are working on is to hide host secrets, so you just simply could never load anything secret inside the host while you're treating a couple of VM exits. So this is all happening in the background, so expect more things to happen for L1TF. And then I have a demo that we're already 10 minutes over time. No, actually we're not. We have 1 minute over time. Oh, less than over time. Ooh, awesome. So I will just quickly show you the demo, run it in the background, and you can raise your hand, and I think we have 1 question or so, or 2, that we can work on. Hands? Any hands? No hands? Okay. So this is a machine I have flying around. I didn't change the host name again. Oh well. This is a machine I got where I just knew this is Garlic and this is exploitable. Where I'm running this as on the host. So you see I'm root over here. I'm running on my 1 thread of core 1. I'm running a program that basically just goes and reads a secret in a loop. Pretty simple. It could as well be a SSH client. And on the other thread of that same core, which is here, right? It's a 4-core system. The second thread of the first core is then CPU 5 in Linux. I'm running a KVM virtual machine that is trying to read that data out using TSX. And I'll just run it in the background. I hope it's not crashing again. And then in the background, like while that happens, did anybody raise their hand now? No? All right. Yeah, doesn't work. It doesn't even start the VM right now because there's an NFS kernel loops on that system. So that didn't work. I guess, no, root. So I guess I can just show you that running as root instead of as a user. But it works the same as a user if your NFS infrastructure would actually work. So here we found, we actually already found the secret. There you go. We could just read the secret in no time from that other thread on the same host. L1TF basically means you have immediate exposure to all data that happens on the other thread. Thank you.